So moving right along in this very brief introductory chapter, let's look at some of the characteristics of the atmosphere. Again, these are very basics you have seen already probably in high school, if not college physics. Earth is obviously rotating around its axis. The axis is tilted, which we will see, which gives us a seasonality, as we will see. So the rotation rate is obviously once in 24 hours. So you can convert that into a rotational speed, which turns out to be 7.27 times 10 to the minus 5 per second. That's radians per second, right? How many degrees you cover. Surface gravity, acceleration of gravity, 9.81 meter per second squared. We will see soon in the next slide that the thickness of the atmosphere in the ocean are relatively small compared to the Earth's sphere, and the change in the gravity with altitude or depth are relatively small as well. So we can, for all practical purposes, assume that gravity is constant within the column of the atmosphere or the ocean. Mean radius 6370 kilometers, mean radius, right? Obviously it will turn out that the rotation effects are important in terms of the local radius from the axis. Since it's a sphere, obviously it becomes smaller as we go north. That's what creates angular momentum instabilities as well. Surface area of Earth's disk. What is that? Basically, if you take let's say a tennis ball and you flash a light at it and look at its shadow on the wall, it's going to project a circle in the shadow, right? A sphere projects a circle as a shadow. So area of Earth's disk is like Earth's shadow. Why is that important? Because it turns out that that's what determines how much sun's energy is intercepted by Earth. Okay? Energy intercepted is going to be the area that Earth projects to the sun as a disk. It's a circular disk because Earth is a sphere, right? So the other factor that's important in terms of atmospheric character, which is also true for the ocean, is that compared to the planet on which ocean and atmosphere are circulating, the thickness is very small. So 6370 is the average radius of the Earth. The height of the most of the atmospheric mass is within order 10 kilometers. So it varies from 12 kilometers in the tropics down to 8 kilometers at the poles and so on. Nonetheless, the order of magnitude is 10 kilometers. Obviously, ocean is also on average 3 to 4 kilometers. So, right? That becomes very important. Why? It turns out that it leads us to something called a hydrostatic balance, which means in the vertical, the motions are at a much smaller scale than in the horizontal. Remember, the Earth's surface is where the atmospheric circulation is happening. The winds can go all around the Earth. Obviously, that's a very large scale, but if the height of the atmosphere is only order 10 kilometers, then the vertical motion is very different than the horizontal motion. It allows us to make certain assumptions by scaling arguments or dimensional arguments, as we will see, which leads to some great simplifications and some great constraints as well. This is just showing the topography for reference. So there is Antarctica, about 3,000 kilometers high on average, and there is the Pyrenees and Atlas Mountains. I'm surprised this doesn't show Mount Everest, which is the tallest mountain. But the main point here is that if you go into the ocean is not very smooth. Ocean has mountains that are actually taller than the mountains on Earth. And ocean is much rougher, as you can see here. Why? Because the erosion, even though water is very heavy, it moves very slowly, especially as you go deeper. where the motions are so small, it's just few kilometers per year, so you can't even measure them directly. That's how slow they are. So the erosion compared to land will be much weaker over millions of years that Earth has formed, or Earth has been changing. On land, you also build glaciers which carve out lakes, and they carve out fjords, and they scrape out stones, rocks, and so on. So the Earth's surface has got different topography, smoother in some sense than the ocean bottom. The most important atmospheric constituents, obviously by molecular weight or by percentage, nitrogen and oxygen make up most of it, with a little bit of argon, and then you have all these other much smaller amounts of gases that are still very critical because they affect energy balance, right? These are inert gases, and well, N2 is inert, but O2 is obviously not, but we'll see that their structure makes them basically not a big player in greenhouse gas effects, greenhouse effect on Earth. But even the small quantities like only 0.5% or 0.0 of water vapor, 0.04% of CO2, N2O, ozone, depending on where the ozone is, carbon monoxide, methane, and so on. They turn out to be very critical because even though they are in trace amounts, CO2 is in parts per million by volume. This number keeps changing every year, whereas methane is in parts per billion. So you can see this is 2 orders of magnitude smaller than CO2, 3 orders of magnitude, right? So these things matter. Why? Because we have started perturbing the radiative balance of the Earth's system. We have started emitting carbon dioxide by burning fossil fuels. This is the famous Keeling curve you would have seen for sure many times. If not, you know that the carbon dioxide started to be measured by Charles Keeling on Mauna Loa in Hawaii based on advice from his advisor Roger Revelle in the 1950s, and soon it became obvious that even though there is this year-to-year breeding of the planet, there is this steady increase in carbon dioxide. So by the mid-70s, Wally Broecker began to shout that global warming was here. Wally Broecker was a famous geochemist from Columbia University's Lamont Doherty Earth Observatory, passed away recently, a giant in the field of geochemistry and climate. Okay, what's this happening here in a seasonal time scale? During the winter, if you look at the average CO2 of the Earth, photosynthesis drops off after fall into winter months because at high latitudes light becomes a limitation. So leaves begin to drop and photosynthesis goes down. So CO2 begins to drop from the summer into fall, winter months, and as sun comes up, spring arrives, photosynthesis begins to pick up. So I said it wrong. CO2 begins to increase. As photosynthesis happens, it's being taken up by the plants and being drawn down from the atmosphere, so it begins to drop off during the summer months. So it increases because photosynthesis stops during fall, winter months, whereas it drops during photosynthetic months. If I made a mistake, you know what I mean, right? So that's a brief introduction to the structure of the atmosphere. We'll look at more and more details, but these are the backgrounds we need to have as we go slowly towards the equations of motion. We cannot do the dynamics without the equations of motion, so obviously that's where we want to head.